In this video, I'm going to talk about isotopes. I'm going to first define an isotope, giving a couple of examples. Then we'll talk about relative mass, radioisotopes, and the half-life of radioisotopes. Firstly, to define an isotope. Isotopes are different forms of the same element with a different atomic mass. So to be the same element, we know that they have to have the same amount of protons, because the protons are what defines an element as being that particular element. So to have this different atomic mass, what needs to change is the number of neutrons that are present in the nucleus. So for example, hydrogen has 3 different isotopes, all of which have 1 proton, as hydrogen has 1 proton. So hydrogen 1, which is the most common isotope, in the nucleus we find the 1 proton, and that's it, there's nothing else. However, in hydrogen 2, which has an atomic mass of 2, in the nucleus we find the 1 proton plus 1 neutron. And in the less rare hydrogen 3, we have the 1 proton in the nucleus, but this time we have 2 neutrons, and which brings it to an atomic mass of 3. So these are 3 of the isotopes of hydrogen. Now most elements have a number of different isotopes. However, the abundance of these isotopes changes. So for example, carbon has 3 different isotopes. Carbon-12 is the most common isotope, and it has 6 protons because it's carbon and 6 neutrons making up the rest of the 12 in its atomic weight. Carbon-13, on the other hand, is less common. It again has 6 protons, but this time it has 7 neutrons, making the atomic weight 13. And the even more rare, in fact it's only about 1 in 1 trillion, carbon-14 has the 6 protons, making it carbon, and 8 neutrons, bringing the total mass to 14. So looking at the relative abundance of carbon, 99% of the carbon that is found in the world and in your body is carbon-12. However, 1% of that is carbon-13 with that extra neutron in the nucleus. And then there are very, very small trace amounts of carbon-14. Now, carbon-14 is produced in the ionosphere when a cosmic ray hits a carbon atom that's floating around up there. Then that's why they're so rare. But also they're unstable, so that over time they decay, meaning there hasn't been a lot of them building up on the Earth. This is where relative mass comes into it. So we talked about the relative abundance. Well, when we look at the periodic table, it has a number for the atomic mass, and it'll be, for example, for carbon, it's 12.010. So this actually takes into account both the isotopes that are around and the relative abundance of those isotopes. So there's 99% carbon-12 and 1% carbon-13. So the relative mass of carbon is 12.01. So it's that 0.01 shows the 1% that's in carbon-13. And this is why different elements in the periodic table will have atomic masses that aren't whole numbers, because we know that the atomic mass is the number of protons plus the number of neutrons, but you can't have 0.01 of a neutron and you can't have 0.8 of a neutron. So this is where that decimal point comes from. It's showing a relative mass as to the relative abundance of that particular isotope. Okay, so it's mentioned before that carbon-14 is unstable, and it's what we call a radioisotope or a radioactive isotope. And what happens with these radioisotopes is that they decay over time. So what's basically happening is in the nucleus, because of the number of neutrons as opposed to the number of protons, as the nucleus gets bigger, the forces holding the nucleus together become weaker. So it becomes a little bit unstable and can fall apart. When this nucleus falls apart, it releases energy, and this is in the form of nuclear radiation. And we'll look in another video about the different forms of nuclear radiation. The time that it takes for half of a substance to decay or fall apart, as we talked about in the last slide, is referred to as the half-life, or the life for half of that element. So for example, if we have, say, a kilo of carbon-14, one half-life later, there's only going to be half a kilo left of that carbon-14. What's going to happen to the rest of the carbon, so the other half a kilo, it's actually going to turn into some different compounds. So as it decays, it actually turns into lighter compounds. Now, different elements have different half-lives. So for example, potassium-42, which is an isotope of potassium, it has a half-life of 12 hours, which in the scheme of things is quite a short half-life. While uranium-235, which is used in nuclear power stations, it has a half-life of 703 million years, which means that if you have a kilo of uranium, the time it takes for that kilo of radioactive uranium to decay into half a kilo of radioactive uranium is 703 million years. So that's a really long time. Now, if we look at this diagram over here, this is what we call a decay curve. So we can see that, say, we're talking, actually, let's talk about potassium. Okay, so here at N0, or time 0, we've got our, let's call it a kilo of potassium. 12 hours later, or one half-life later, that kilo of potassium is going to have decayed into half a kilo of potassium. Another 12 hours later, or another half-life, that half a kilo is going to decay into a quarter of a kilo. And then the third half-life, that quarter of a kilo is going to decay into 1/8 of a kilo. And this keeps on happening over and over. In this video, we've talked about isotopes being versions of an atom that have the same atomic number but a different atomic weight, therefore a change in the number of neutrons. We've looked at relative mass being the mass that's shown on the periodic table, which takes into account the relative abundance of the different isotopes. We've talked about radioactive isotopes that decay over time, producing nuclear radiation. And we've talked about the half-life being the speed at which those radioisotopes decay, and in particular, the time that it takes for half of the atoms present to decay.